All right, the last talk in the session this morning is Swastik Mita, who also comes to us from North Carolina State University, and he's going to tell us how we put some quantum in OpenMP.
Thank you for the introduction. So, morning everyone. Today I'll be presenting about OpenMP-Q, which is framework or extension to OpenMP for quantum task offloading. And this work is done in collaboration with my co-author, Atulya, who is graduated from NC State as well, and my advisor, Dr. Frank Miller. So what's the motivation behind OpenMP-Q? And we all are aware about HPC, that is high performance computing, and HPC is used to solve numerical problems. These problems are computationally intensive problems, and most of the times we use accelerators to solve such problems. Now we have a new accelerator in the picture, that's quantum computers. And quantum computers prove to have or potentially have much lower time complexity than these other accelerators. For example, Shor's algorithm, if you're aware of quantum computing, it's a very common algorithm, which basically says that we can factor an n-bit integer in polynomial time. Then Craig Kidney was able to provide an estimate that a 2048 RSA integer can be factorized in 8 hours. This is basically the crypto, if we use 20 million qubits, but this is an estimation. Then we have another example, Google Sycamore, which is a Google quantum processor, was able to sample a specific random circuit in 200 seconds, which would take approximately 2.5 days for a classical computer. So now, if quantum is so good, then why do we not see any quantum HPC integration yet? And the issue is still now, at least until recently, quantum computing was a lot of the programming frameworks for quantum computing were written in Python, and a lot of HPC frameworks are written in C, C++, like OpenMP. And because of this, there was a lack of interoperability, and which we cover using OpenMP-Q. So before moving on to OpenMP-Q, what problems can quantum device solve? Because clearly they cannot solve all the problems as other accelerators or classical computers. And why is integration even relevant? Like, why can't we just, if quantum is so good, why can't we just push everything to quantum and remove HPC out? So now your NPC problems, which are non-polynomial time problems, can be executed on a quantum computer using a method called VQE, that is variational quantum eigensolver. And the idea of this method is that the execution on the quantum device should result. And for this, what we do is we take a parameterized circuit or a sequence of quantum gates, execute the quantum device, and that we retrieve some qubit frequencies. Now, these frequencies are sent to the classical optimizer for optimization or post-processing, and then this process is repeated in a loop. And this classical optimizer is basically your host, and this dominates this loop, which basically addresses us that HPC is needed because the classical optimizer can be done by HPC, and if we are reducing the performance, if we are increasing the performance of the whole problem solving, then it's much more efficient to have the classical optimizer as HPC and the rest of the part being done by quantum. So, for example, max cut problem, which is again an NPC problem, can be deployed on a quantum computer where a graph can be encoded as an Ising Hamiltonian. And this is how the pipeline of the problem would look like. There will be some initial parameter values, or you can say angle values, which will be fed to the parameterized circuit within quantum, that's ANSATs. Quantum execution will give you some bit strings, and you can use this bit strings to estimate the cost, and then you can run a classical optimizer to reduce the cost, and this can be done in multiple iterations. Another example is quantum error correction. Now, in quantum error correction, we have quantum computers which measure the encoded qubits to detect errors, and then this is again sent to the classical optimizer to apply correction on those qubits. And now these need to be done in real time, because if it's not done in a certain time frame, then the qubits will lose its coherence and error correction wouldn't value much. And we see that now HPC also has real time. We saw in Braden's work that OpenMP-RT provides real time capabilities to HPC. So hence, the conclusion from here is that quantum or HPC alone are not enough. We need quantum for much faster processing, and we need HPC for faster processing of classical optimizer. So this image is taken from Oak Ridge Lab to show the pipeline of quantum tasks. You have a simple HPC application, which could be basically VQE, which is deployed on a quantum computer using quantum libraries like Qiskit or Q. These libraries generate a quantum task, they pipeline the quantum circuit, convert the code into quantum intermediate representation, QIR over here, and then deploy it on a quantum processor. Now, where does OpenMP-Q come in? If you see the top two layers, HPC application and Qiskit, now we are trying to basically say that HPC application is your classical optimizer, and you have these quantum libraries, and we want to build an integration between the two. So that is OpenMP interacting with the quantum device. So to understand OpenMP-Q, we'll first look into how quantum execution looks like with Qiskit. So the pseudocode on the left is basically executing quantum tasks using a series of quantum gates. If you see on the left, we have C0 and rotation gates applied to the qubits. Now, Qiskit is an open source Python quantum library, and it's used to create parameterized circuits. We'll again look into the pipeline we saw before, that there's a parameterized circuit executing a quantum task, which is right there in the Python pseudocode. And then there's a classical optimizer which updates these values based on the results and feeds it back to the quantum device. So the process is repeated in a loop over there. Now, Qiskit is not the only quantum Python library available. And in fact, it's not just the Python libraries. For example, we also have QASM, which allows assembly level programming with quantum. But integrating QASM and HPC won't be easy as well. Now, there is also CUDA-Q and Intel Quantum SDK, which are C++ based libraries. And it would be much easier to integrate OpenMP-Q with them because they both are in the same programming language. But unfortunately, till now, CUDA-Q is not supported by all the quantum hardware. And also, it's not like we are replacing or so these are lower level quantum libraries. And even if we have CUDA-Q, we would still want OpenMP-Q on top of that for ease of parallelism, because the user might want to have a finer parallelism at the classical optimizer level. So the next question is, how do we extend OpenMP to also provide quantum device as a target offload? And then for now, we are reading into how do we execute the underlying Python framework, but this can later be modified into underlying CUDA-Q or any C++ framework which is available later. So we'll first look into what a basic OpenMP offload pipeline looks like. There's a user code, the user would initialize some data, then there'll be a pragma OMP target region within OpenMP, which will offload this to any accelerator. Then the data is passed to the OpenMP runtime using the map clause. And then you have memory operations, for example, QDAMM copy, kernel execution, and then data is mapped back to the OpenMP and back to the user code. Now, if you want to introduce quantum offloading in this, there are a few extra steps we need to do. User also needs to provide the quantum gate sequence. Then we also need to retrieve the quantum gate sequence. Then we need to wrap these quantum gate sequence and the initial data values to pass to Python. We need to invoke the Python code or invoke the Python library, which is there below for interacting with quantum. Now, Python library will take care of memory operations and kernel execution and quantum, but then we need to retrieve these quantum results back to OpenMP, run a classical optimizer, and so on. So again, how do we make sure that OpenMP runtime knows about the quantum gate sequence provided by the user? And then how do we do the C++ Python interaction? And then how do we do the synchronization between C++ and Python? So from what we have now, we look into the first problem we saw here, the OpenMP runtime interaction and retrieving the quantum gate sequence. What we do is we create a quantum circuit library, which basically provides you C++ functions for quantum gates, for generating the Python code, for executing the Python code, and we embedded it within OpenMP, in fact, within the offload section of OpenMP. Now for a user, user can create a quantum object. Yeah, so user can create a quantum object as we see in the code over here. And then we also provide an additional clause, that is the circuit clause, to pass a pointer of this quantum object to OpenMP runtime. So now since there's a pointer of the quantum object passed to OpenMP runtime, so any changes made to this quantum object would also be reflected or visible at runtime because it's now like a global memory space. So this allows the interaction between the OpenMP runtime and the user code. So from what we have right now, this is the first phase of our design. You have a simple OpenMP code, and if you see the code on the right, a user creates a quantum circuit object, and then it passes the quantum circuit object in the circuit clause. Then OpenMP runtime retrieves the angle values or the initial parameter values for quantum device from the map clause. And now the idea is, how do we generate Python code from this? And then how do we get the quantum gate sequence which user has provided? So we allow the user to execute the quantum gate sequence within the offload region. For example, the VQE function over there, which basically again allows the user to access the quantum circuit library to provide the sequence of gates, for example, rotation gates or C0 gates, and any number. And these gates are now, these gates information are stored in the quantum object, and then our quantum circuit library generates Python code for these gates, and then later on it will invoke Python to execute the quantum task. Now, before we move on to how Python invocation happens, if we see the code before, it's kind of, it doesn't feel right, because if you see there's a loop, repetition loop over there, but then you're again and again creating a quantum circuit object, you're again and again deploying or executing a quantum kernel, initializing a quantum kernel. And if you're talking about generating Python script and executing it, you're basically doing it on every loop iteration, which doesn't make sense. So to fix that, we utilize the OpenMP reverse offload. If you see the problem before, again, it has the parameterized circuits executing quantum, then the cost estimation, and the whole thing is repeated. And this repetition, again, as I said, would cause a lot of cost and time for repeated execution. So for that, what we do is we utilize OpenMP reverse offload. Now, reverse offload allows us to execute the target region only once, and then it provides this target ancestor, which makes sure that you can copy data, you can update some data within the OpenMP, and then push it back to the quantum kernel, and the quantum kernel won't be reinitialized. In fact, the same quantum kernel will execute again. So basically, you can run your classical optimizer here and can send the modified angle values back to the quantum kernel without executing or invoking Python again and again. Now, there are a few changes we need to do to make sure this works. First of all, we want the user to not initialize the quantum gate sequence again and again, because we'll be using the same quantum gate sequence. So for that, we push the VQE function out of the target region. And since VQE is utilizing the quantum circuit object, which is also available at OpenMP runtime, so user can make any updates over there and runtime can still see it. Similarly, we also push this for loop or the repetition loop inside the target region, because we want to avoid invoking or initializing quantum kernel again and again. So the repetition is basically now just doing the memory transferring the updated angle values to the quantum circuit, then executing the quantum code, then the qubit frequencies fed back to the classical optimizer, and so on. So now the question is, how do we synchronize the C++ and Python code we have? Because now Python code cannot stop its execution. It needs to read in the new values as well. So for that, we utilize the Unix pipes within kernel, within Linux. Unix pipes are basically used for bidirectional communication between our OpenMP and Quantum Python library. This is like a parent-child process. So if you see the figure on the right, the OpenMP executes a fork call to create a child process. And then using this, we create two pipes, pipe A and pipe B. Now, one end of pipe A is used by C++ to write, whereas the other end Python process or the child process to read, and similar pipe B doing the other way around. Now, within OpenMP, you'll see once a target region is called in Python is invoked, we have a write call. And if you go back to the Python code before, there was a read at the top of the loop. And this is how Python makes sure that it initializes, but it doesn't start till the time it has the initial angle values. So it reads the initial angle values or the updated angle values, execute the quantum code, and then the results from the quantum device are being fed back to OpenMP, and OpenMP reads it using pipe B, then updates the angles, the classical optimizer steps, and then this process keeps repeating. And this is how we are synchronizing the C++ and Python code. So this is how the whole pipeline looks like. We have an OpenMP user code. The user would initialize the quantum object, would provide the quantum gate sequence, and then call an OpenMP runtime. Now, within OpenMP runtime, the initial angle values are stored within the quantum object. Then, based on the gate sequence and the angle values, a Python script is generated. Now, again, the Python script, first the quantum circuit library invokes a Unix bridge, and then it executes the Python code. Now, this process is now repeated in a loop without initializing the quantum circuit and generating the Python script again. Now, there's a common problem in neural networks of local minima, and for that, the initial parameter values need to change. So you would want to run multiple experiments of this repetition. So for example, you would want to run multiple VQE with different initial values. And for that, we provide multi-QPU. So the idea is, what if you have multiple quantum devices? So you can use each of those quantum devices to run different VQEs, but with different initial parameter values. And since OpenMP is basically SPMD style programming, we utilize the OMP parallel to run the whole same code. And one change which we do is we store the angle values in a 2D array, if you see on the top over there, so that every thread is working on a different memory, and hence avoiding race condition. Now, this whole multi-QPU can also be integrated with reverse offload. So to make sure there is no reinitialization of quantum kernels. Okay, so some of the common queries we had when building OpenMP-Q. First one is, why don't we utilize OpenMP interop? Because we are solving the problem of interoperability. So the idea is, for now, we assume that the Python libraries within Quantum support all the quantum hardware right now, or the simulators. And we do not need an access to streams of queues like in case of CUDA. We are simply generating a Python code. So interop here wouldn't make sense unless we have C++ based quantum libraries, and Quantum gives us access to the queues within it. Also, at the same time, by this implementation, you can generate any Python code, not just Qiskit. Could be any code, could be just a C++ code, hence avoiding specific vendor APIs. But at the same time, OpenMP interop is also a solution. We can use that. Another query is, in case of OpenMP, if, for example, if you're using any other accelerator, you can offload it to an accelerator, and if the accelerator is not available, OpenMP will run the normal classical task for you. However, OpenMP-Q wouldn't handle that. But if you see the type of problems you are trying to solve, there is no use if a quantum device is not available, because those problems on a classical system would take forever. And also, we kind of provide this ability because the quantum execution can run on a simulator if there is no quantum device available. Another was, now we talk so much about Python libraries, but CUDA-Q and Intel Quantum SDK are these C++ libraries, which will have a much easier integration with OpenMP because you won't have to generate a code and straight away call those functions, which is true. It's not that OpenMP-Q restricts to only Python code generation. It can definitely be extended to call CUDA-Q instead of generating a Python code. And also, the user, as we discussed before, the user would still want some ease of parallelism, which OpenMP provides, like in case of multi-QPU, and then could utilize these libraries as an underlying layer, because if you see, even Qiskit uses Rust below the Python API. So it's kind of the same thing. So moving on to experiments, again, we saw the VQE method. There is ansatz operation, expectation estimation of quantum qubits, and then classical optimization step. So we evaluate OpenMP-Q using this VQE implementation. We do 1 to 6 VQE runs. As we saw, we need multiple VQE runs with different initial parameter values. We do 80 iterations of each run for getting a better, lower cost estimation. And we run this serially, then we run this parallelly over multiple QPUs, and then we run it using a reverse offload style execution. So the first graph shows results or runtimes for multi-QPU. If you see the bar graphs, the box plots on the red are basically execution time values without multi-QPU for 6 runs. So for 6 runs to complete, it took 143 seconds. Whereas if you had multiple quantum devices, it runs all the 6 simultaneously, it takes only 49 seconds, giving us a 2.9x speed up. Then we have reverse offload style execution. The same values for single VQE runs on the red. And if you see, if we get rid of all those initializations from Python code generation and invocation, then we are able to achieve 126x speed up because the cost of rebuilding is a lot. And we also compared reverse offload style execution to simply executing the quantum code using Python without all the OpenMP. And that overhead is just 0.05 seconds with all the ability of OpenMP you get along with it. So now all those runtime values don't prove much correctness of OpenMP-Q. So we also studied the cost estimation of all the 6 VQE runs separately. And if you see, the cost estimation reduces after 80 iterations for each VQE, which basically demonstrates that our OpenMP-Q is running correctly, as this is what we expect. So I conclude by saying that we have now OpenMP-Q, which is like a lightweight extension to OpenMP 5.x target model. And this treats quantum processors like any other accelerators for current OpenMP target. And we provide a circuit clause which allows the interaction between the OpenMP runtime and the user code. And then we also provide POSIX bridge for communication between the Python and the C++, or it could be any other quantum library, and the OpenMP C++. And we observed that we could achieve 2.9x speedups with multi-QPU and 126x speedup if we do a reverse offload style execution with just 0.05 seconds of overhead of running OpenMP, with all the benefits of OpenMP along with it. If anyone wants access to the code, I have put the GitHub link over here. And if anyone wants to hire a PhD engineer, then I have also put my website over.
Thank you.
Thank you, everyone.
We have a question for our speaker.
Excuse me, but I'm a skeptic of interpretive languages. So why do you use Python? Why don't you just go straight to an HPC language like C++?
So most of the frameworks were built on Python. And CUDA-Q, I think, was in 2022. And CUDA-Q still does not support all the quantum hardwares or the simulators. And so, I mean, the basic idea was...
You've got no way out.
Yeah, I mean, the basic idea was that currently we don't know how Q is going to proceed, how they're going to build on this,
Okay,
how better is going to get.
that
So
makes sense.
So,
It's more of a back-end question.
right, yeah, I was gonna say, I think that, as I understood what you presented, it's kind of independent of whether it's Python.
Right.
That's,
Yeah.
you're saying that, okay, currently it's Python, but the kind of underlying problem that you're trying to solve is the fact that you can't, so is it a Python limitation that you need to be generating the quantum circuit dynamically, or? Cause I don't understand.
It's not. So as I said, that Q can also be the underlying layer.
Right,
Or
so
it could be
so you need to, because the gates actually change the quantum program, you need to have those, and those are kind of dynamically configured from it.
Right. I mean, that can be just scalable. You can just add those in the quantum
Right,
circuit.
but there is a part of it that's still kind of repetitive and offloaded. So what occurs to me is, have you thought about creating some kind of object that is your kernel, right? So normally, right, the kernel for like GPUs, you're gonna generate the kernel statically, and then you have this,
Right.
you know, binary for the GPU that you're gonna load and execute, and you don't need to like keep generating that. But there's still this piece that's kind of static in some sense for what you're doing. But there's enough of it that's not static that, yeah, it's okay, maybe you're not gonna pre-compute that, but your reverse offload stuff is interesting, but it also seems that there could be value to being able to generate that static piece and then refer to it throughout your program. And
Then you have problems baking in some of the initial state you want to, which some one was just not used to.
well, yeah, I mean, it's what I'm suggesting is you kind of do a separation of concerns and get an object that represents that kind of consistent piece. And then all of the other, like your reverse offload stuff is still needed to optimize building the circuits, even when, you know, but you know, if I'm calling this thing 5 different locations in my classic code, I could get some of the benefit, at least of the reverse offload, by having that object and being able to say, well, go use that object that I already put over there. It's another mechanism to kind of get at the same thing you're getting at with the reverse offload.
True. I mean, this is possible, but for example, now your quantum, in case of GPU, as you said, you create a kernel and then you can reuse that kernel. That won't happen in case of quantum, because we are still doing the quantum process execution again and again. But that is true that if you have any other a piece of code which is looking for the same quantum gate sequence, it can just access the object and doesn't have to recreate it. The Python code doesn't have to be generated for that again.
Right.
And then
Maybe let me comment a little bit on the status quo in quantum computing. So you have to understand that this comes from the physicists who don't know much about coding or then learn about software engineering and start with Python. So everybody uses Python right now. But this is just the backend. We're providing a front end over here. So you can replace it with any other backend. And when it comes down to the physics experiment at the very bottom of the stack, you have an FPGA that interacts with lasers or microwave frequency generators. So there is code, in this case, actually synthesized code, that is imperative in some sense and not interpreted at all because it has to have very precise times. So the question is just, can we build in the future a stack in the middle that will also use more performant languages? And the answer is this will certainly come at the time when these machines actually scale to some larger point where they need to have that kind of infrastructure in between. So today, it's kind of like sort of like rapid prototype where you take an interpreted language just to really compile an FPGA schedule. But tomorrow, it could be totally integrated and everything might be C++ or Rust or something else, and the node cares. But that gives you a lot more predictability and would still allow the CUDA-Q paradigm to survive.
Complete fortune.
Yeah, so I agree with everything you're saying, Frank, but the point I'm driving at is actually there is another general kind of OpenMP concept that we have not yet supported yet. So like, I say declare SIMD, right? There's actually a function that gets generated there, and you can't get a pointer to that function, and you're looking kind of sort of for the same thing, right? Like, I'm going to generate a function for you, and I want to hand this back to you so you can like go and use it around in your program.
In fact, we can even use it now because this one shows you have different iterations, and each time you actually start off with the same state, just to clarify that, but then you perform different rotations. So there are these parameters in there, and there is actually already work that creates parameterized pulse schedules inside the FPGA. So you could take this object and send it to the FPGA, and it just modifies the table's schedules. It's very easy to do. But we can do more with that object, I think, and I totally agree with you. It could encapsulate the entire middle layer.
All right, it seems like we're going to have a lot of great discussion at lunch. Let us thank our speaker again.